Okay. Hello, everyone. This part here is proteins and peptides part 2C1 or CI. And so last unit we talked about the biological synthesis of peptides. So what we're going to focus on today is the chemical synthesis of peptides. And it's divided up into three main sections. So hold on a second. Yeah, three main sections. So we're going to first spend time looking at protective group strategies, and then in a subsequent session we'll look at coupling agents, and then something called solid phase peptide synthesis. All right, so let's talk about protecting group strategies. What are protecting groups? Why are they important? Why do we need them? But before we do that, let's maybe first spend a bit of time talking about the chemical synthesis of peptides, and why this is important to do that. Because last unit we talked about how biology can actually make peptides really efficiently and really, quite easily. I mean, there's essentially, billions of years of evolution aside that has been optimized to make peptides. So why should we, try to reinvent the wheel using chemical synthesis strategies? Okay, so I've outlined a few things here. So why synthesize peptides? Well, biologically, this is also relevant as well. We want to also use peptides to study their biological function. Many peptides act as hormones, potentially neurotransmitters. Some are antibiotics. We can look at anti-cancer agents. We can look at how medicinal agents, new drugs that are in clinical trials, how they inhibit certain peptides or proteins. This is really important, right? To be able to have access to a lot of peptides and proteins. Since the turn of the century, there's actually been a lot of new therapeutic agents that have been identified and discovered, and there are around 70 to 80 approved therapeutics that are actually proteins, that are protein based, that are used to target various types of cancers, different diseases. Right now I'm working in my home, and you're of course well aware of COVID-19 and the impact that has had. Well, researchers and scientists want to study those proteins from the virus and how they are maybe involved in the life cycle of the virus, or how that could be used as potential ways to target the virus. Okay, and the reason we want to chemically synthesize them is because we want to be able to perhaps scale up the synthesis of these to look at things like structure. Okay, so this requires a large amount of protein to study, again, the pharmacokinetic parameters. And lastly, it's not mentioned here too, but often we want to change the structure of the peptides in such a way that we can add different chemically modified amino acids to perhaps increase the lifetime, the potency, and the overall attributes of that peptide. So there's a large interest in being able to chemically synthesize peptides. Okay, so how do we do that? Well, there are two sort of main approaches. One is to use something called a solution phase synthesis, which we'll talk about in the next couple sessions, and then finally a solid phase synthesis, which I'll talk to you at the last unit. Both use something called an activation protection strategy. And before we talk about that, we've already learned actually about activation, right? Recall, this involves taking those carboxylic acids that are really inert, making them more active, such as active esters. And now we also need to consider protection. So what is protection? What is a protecting group strategy? What does that actually mean? So here are the 20 most common amino acids. And, in the ribosome biologically, different tRNAs bring these at the right site at the right time. But if you're to make this chemically, you have to think about what amino acids have side chains that could act as potential nucleophiles. So if you look at glycine and alanine, you can see here that both of these hydrogens and these methyl groups here, they're inert, they're not reactive, so you don't have to worry about that. But as soon as you start looking at things like serine or threonine, now you have this hydroxyl group that is a potential nucleophile. Other potential nucleophiles include things like cysteine, that sulfur is an excellent nucleophile. You don't need to worry about these ones because these are aliphalic side chains. This sulfur here on methionine is not especially nucleophilic at all. Proline is not nucleophilic. Phenylalanine is not nucleophilic. But tyrosine has a hydroxyl group here. That's a potential nucleophile. Tryptophan here has amine here, a couple lone pairs. That is a nucleophile. You also have to consider these as nucleophiles because when they become deprotonated, that negative carboxylate can act as a nucleophile. Moving onwards, asparagine, glutamine. These are also potential nucleophiles. Even histidine and lysine, when it removes its proton, and arginine, potential nucleophiles. So you can see that just the side chains alone, we have 5, 9, 10, 11, 12. More than half of them have potential nucleophiles. So that could very much impact the chemical synthesis when we have to consider our amino acids. So this is where we need to think about something called protecting groups and how we can use protecting groups in organic synthesis to get our desired product. So what is a protecting group? So you may have heard this before. It's ubiquitous in organic chemistry. It's a functional group that's reactive in a subsequent step, or a functional group that is reactive in a subsequent step is transformed into another functional group that is not reactive in the subsequent step. So that's a little bit of a mouthful. What really this means is that let's say you have functional groups here, A and B, and what you need to do is you want to react A to some other functional group, we'll call that X. However, B could also react with functional group X. So what you need to do is you need to protect B with a protecting group. And we'll just abbreviate that PG. All right, so once we do that, we now have A, functional group A, we have a protecting group. And this is where we can now do our desired transformation of A to X. Now finally, we have our desired transformation, but we have this protecting group still on there. So the last step now involves removal of the protecting group to go back to that original protecting group B. So now we need to remove the protecting group. Okay, so there are some general criteria that's important to consider when we're dealing with a protecting group. So again, let's use some protecting groups or some functional groups that we have seen already in class. So here is a a group or some big molecule with a carboxylate, and then we have an amine group here. So in order for us to do this transformation to go from a carboxylate to an ester, we need to take into account the amine here. So first thing we'll do, and I'm just going to use just very layman terms. I'm not going to assign any chemistry yet, but the approach is going to be the same. So let's protect the amine with a protecting group. And then now we're going to take that carboxylate and react it to make an ester. And then number 3, remove the protecting group to regenerate the amine. Okay, so there are 3 general criteria for a protecting group scheme that you need to keep in mind. Number 1, transformation of the original functional group to the protecting group must be facile, it must be easy. You don't want to spend a lot of time doing this chemistry. So it must be facile, and I would also mention high yielding. The protecting group must be inert to the conditions of the subsequent step. It makes no sense to put a protecting group on if it cross-reacts or gets removed and then reacts. So it must be inert to the conditions of the subsequent step. So you need to think of this in advance of your chemistry. Number 3, this one is often overlooked, but it's just as important as number 1. Deprotection of the original functional group must be facile and high yielding. So you don't want to spend all this time now trying to remove the protecting group, or furthermore trying to remove it and then you run into side reactions. So you want to have something that's easy to put on and also easy to come off. Okay, so in general we can divide protecting groups into acid or base labile protecting groups. Okay, I mean there's certainly other kinds and flavors, but the one that we'll be talking about the most, or I guess now as an introduction, is an acid labile carbamate that is used to protect the N-alpha group of amino acids. Okay, so again, just to recall, your amino acid would look something like this. And then what we need to do is we need to find a way to protect that N-alpha group. So a really nice way to do that is to use something called the tert-butoxy-carbonyl group, also abbreviated as TBOC. Okay, so this is where the TBOC comes from. So this is how we protect an amine group with a TBOC group. So it's a tert-butoxy group and a carbonyl group. So we take tert-butoxy carbonyl anhydride, which is this reagent here, and we take some sort of base, and what you can imagine will happen is that the nitrogens here, they will come and they will react at one of these anhydrides. You can see that it's fairly reactive because you have oxygens on either side pulling electron density away. It's a symmetrical molecule, so it doesn't matter which one it reacts to. After the tetrahedral intermediate's formed, then you collapse it and you'll generate what is known as a BOC protected amine. It's a carbamate, meaning that a carbamate is a functional group comprised of this functional group together. So this is a carbamate. It's like an amide and an ester blended into each other. So the nice thing about this BOC protecting group, or this TBOC, is that it's easy to install and remove. Okay, so it's easy. Easy to remove. It actually gets removed with acid, and therefore a BOC is a base stable protecting group. Okay, so you'll be hearing a lot about BOC over the next number of sessions. Another really good protecting group that actually has complementary stability and lability is this other carbamate functional group that's also used to protect the N-alpha group of amino acids. It's called Fluorenal methoxy carbonyl group. Okay, that's a big word to say, Fluorenal methoxy carbonyl. That's why it's abbreviated as FMOC. And this is what FMOC looks like. And the way that this is installed is we actually take FMOC chloride, not anhydride, And you already know that these types of functional groups here would be very reactive. Take some sort of base, weak base, and you can imagine now the nitrogen will attack here, electrons will go up, proton transfer, come back down, kick off the chlorine. So what you'll end up getting your F-MOC group attached. So this is also the same thing as NH-F-MOC. So you'll often see this as well. As I mentioned, this has complementary sort of stability profile to the T-BOC that we just talked about. So this is actually a base labile protecting group, meaning it comes off with base under higher pH. However, it is stable under acidic conditions. Okay, so we will be learning about more protecting groups in as we do more synthesis, as we start the synthesis. But for now, I just want to introduce protecting groups and a couple of common protecting groups.